Hello. Hi. How's it going? We're about to actually start drawing, but before we go and do that, I think it's a good idea to run over the underlying big picture concepts, because a lot of this stuff is kind of weird, kind of confusing sometimes to beginners, myself included when I was first beginning. And if we have a good, strong mental model going in, then the coding will be a lot easier. So just a side note, if we're going to render anything, then we'll need another structure called a frame buffer. Now, a frame buffer is basically wrapping up the image views, which will be used for each of the attachments. In this case, just a color, but we could have multiple color attachments. We could have depth stencil buffers and all of that. So we'll have some sort of image view, and we'll have a number of those. Those are the attachments of the frame buffer. Okay, so that's one thing. We'll need to create that. We'll need to know the image views, which will be the attachments, as well as the specific render pass, which the frame buffer will be used with. So that's just one thing to bear in mind. The other thing to bear in mind is anytime we do any work in Vulkan, we actually record commands. So some examples of work could be drawing graphics to an image, presenting an image to the screen, transferring memory. If we want to transfer a bunch of memory from one location to another internally, those are things we would use commands for. And these commands, the way we work with them is we record them in a command buffer, which holds a list of commands, and then we submit that command buffer on a queue. The benefit of that is if we have a whole bunch of commands ready to go, then when we submit them under the hood, Vulkan can sort of reorder the commands and do them in a more optimal way. But in order to allocate command buffers, we'll need a command pool. So if you like, you can visualize your command pool as a structure which can create and allocate command buffers. So we can create one and allocate it. Now, the idea behind the pool structure is it essentially holds a bunch of threads and lets them spin in idle. And the benefit of that is that when you create a thread, there's a non-zero overhead to that. You need to, there's a bunch of resources and performance involved in creating and destroying a thread. So the way you get around that is you have your threads held by a pool, and then they're allocated when needed. And then when they're not needed, they're just returned to the idle pool. Other side note here, this command pool manages the memory of the command buffers. So we do not need to destroy command buffers. We just destroy the command pool, and that destroys all of the buffers. So again, the early part of this video is going to be just a little spattering of information, but it is important. So how could we set up an engine to use commands? Well, the general idea is we have sort of a main program, and then we have a bunch of frames which the program can work with. Who knows? Let's say 3 frames. Okay, now each frame is going to have a bunch of swap chain stuff. So swap chain image, image view, frame buffer, all that stuff. Each frame is also going to have its own command buffer. So when the program says, hey, I want to draw frame number 1, it records the draw commands on that command buffer and submits it. It can record draw commands on a different frame's command buffer and submit that one. That's fine. And then as well as that, we're going to have sort of a main worker command buffer. And that main worker command buffer will be used for any sort of central memory transfers done by the program. All of this will be allocated from a command pool. So we have 4 command buffers, one for the sort of the main workhorse, and then each of these ones here. So this is sort of a high-level overview of how we could sort of start to structure things. But then we get to the actual drawing work, and there's a number of steps, okay? First step, so if we want to draw something, we need to fetch a frame. Then we need to record drawing commands on that frame's command buffer. Then we need to submit the command buffer. And that does the work of actually drawing the, performing all of the drawing commands. Now, the thing is, what we would do is we would actually re-record the drawing commands every frame. That doesn't take a lot of performance. What does take performance is actually submitting the command buffer, and that's fine. We have to do that every frame anyway. And then the last step is we need to present the frame, and that puts it up on the screen. But there's a little bit more involved, little bit more in that. Before I get to the question of asynchronous operations and all of that, I just want to give sort of a diagram of how the whole render present operation works. If it helps, we could think of a series of boxes. So let's say we have a box of idle frames. They're not being used, they're just sitting there. So each of these is a frame. And then what we do is we acquire a frame and then we do some graphics operations on it. Okay, fair enough. So then we can think of another box of rendered frames. And what we'll have after this image has been acquired and drawn to, we'll have a bunch of images ready to go, ready to render. Then we'll grab one of those and present it. Now, this isn't quite how our function is going to work. So we're not going to grab something. We're going to go with the same thing through the whole process. So we'll have one image, we'll render it, and then we'll present it. There won't be an intermediate bin, but it does help to sort of think about that. Anyway, so then we see our thing on the screen. Right, there it is. Okay, but we are also sort of working in mailbox mode. Remember, when we created our swap chain, we created it in mailbox mode. So what that means is there's a limit. There's a limit up here, because what happens if nothing's idle? Then can we acquire anything? No. So the way mailbox presentation works is if the idle section is completely empty, and we have, what do we have? 2 frames have been rendered, 1 frame is being presented on the screen, then we can actually, the acquire operation can actually use an image which is sitting in the rendered box, which is why we can have frame rates above 60 frames per second in mailbox present mode. So that's the basic idea, but anyway, let's go a little bit further and look at the whole draw process. Okay, so the operations which are performed in the course of our drawing function are asynchronous. And what that means is there's a number of discrete sort of steps. We have acquiring an image, doing the rendering, so doing the graphics operations, and presenting. And each of these are done basically by Vulkan functions. And the thing is, two things happen. What happens is the function does its thing and returns, and that actually happens pretty quickly. But then under the hood, the graphics card is working. So the GPU works, and this is slow. So if we were just looking at this from a function perspective on the CPU, this stuff would be breezing through super quickly. However, under the hood, the GPU would still be working at each of these steps. So when we grab an image, the function returns. It might return before the image has actually been properly acquired. And so graphics can't do anything because the result here is not valid. And similarly, if we do get a valid result, then we perform graphics operations. The graphics function returns pretty quickly before the graphics have been fully rendered. And so the result that we get here, if we're just looking at the CPU side, is not really valid for presenting. So for this reason, we need to look at a bunch of synchronization structures. And this is the point where, for beginners, the Vulkan stuff can sound like not a lot of fun. So there are two sort of fundamental synchronization structures. One is a semaphore, and the other is a fence. Okay, so the idea with the semaphore is I think about it like a flag. This is how I visualize a semaphore. Is we have some resource. And often it comes up in multi-threaded programming when you have multiple threads using one resource. So this is the example that I use. And we have process number one is going to do its thing. And then process number two is going to somehow be involved. Okay. But these processes don't know about each other. The only thing they can see is this flag. So what we want to do is we want process number one to signal the flag when its work is done. And we want process number two to be looking at that flag and wait for the signal. So semaphores are really useful when we have different processes that don't necessarily know anything about each other. They just know about that flag. And then the other process is called a fence. And what we do is this is all sort of synchronization within the same process. So when a process gets to a fence, then it has to wait until the fence is opened, until the fence is signaled. And in the meantime, this generates a CPU block. So the process is stalled. And then when that fence is open, the process continues. And then we have to manually reset the fence. Now what's really going to happen is that some other process down here is actually going to be opening the fence to let the flow of execution continue. This will make more sense in a second. So typically we would use, again, semaphores for sort of like a GPU CPU synchronization, and we want to use a fence for sort of pure CPU synchronization because of the fact, see, this is even getting a bit esoteric for me, but the fact that we can open the fence from the same process, if that makes sense. If this gets confusing, we'll just look back at this diagram and remember that this sort of main line can execute incredibly quickly. And these sort of GPU calls are going to be quite a bit slower. Anyway, so let's bring it all together. Let's bring it all together. Again, remember, there are 3 steps. Acquire, graphics, and present. Now, each of these are going to be going out to the GPU. So, for that reason, we have GPU, CPU, synchronization. We're going to put 2 semaphores. Now, the acquire process is going to signal this first semaphore when it's done, and that will be telling the graphics process that a valid image has been acquired. Okay, so we signal this one, and we're going to wait on this same semaphore. Okay, the graphics process is only going to proceed when this semaphore has been signaled and a valid image has been acquired. Then we need to synchronize between the graphics rendering operations and the screen presentation operations. And so similarly, we're going to signal the second semaphore when we're done, and this present operation is going to wait on the semaphore from the graphics. So if we were to name these semaphores, we could call this like whatever we want, image acquired, and render finished or something like that. That's fine. Okay, so the question is, well, what about fences? Well, remember what I said before about the mailbox presentation. It's possible that the next frame that we grab, that we want to render, has already been rendered, and it's actually waiting around to be presented, but we still grab it anyway. That is the benefit of a fence. So remember the other thing that I said, this through line can execute incredibly quickly. So what happens? We have 3 frames ready to go. Bang, bang, bang. We render all 3 of them. Then this is going so quickly that we come through to the pipeline again, and, well, everything's rendered. Well, we still want to be able to run through and still acquire an image and render it. But we want this fence to sort of block that, and we want that to be waiting on the result of the graphics operation. Okay, so we basically want to, after a valid image has been rendered, we want to open up this fence so that if this function executes incredibly quickly, it can go through again, grab the same image, re-update it, and present it. And that's how we're going to get 5,000 frames per second, is because we're not presenting everything to the screen, we're just rendering really quickly. And similarly, what we want to do here at the top, when we come in here, is we want to wait on the fence and then reset the fence. Okay, so we wait, the fence is open, we come through, we close the door behind us, And the reason we close the door behind us is if the function comes in again, we don't want that to be ready until an image has been rendered. Does that make sense? You know what I'm saying. Synchronization structures in Vulkan, sometimes I come across like a crazy person because it's a slightly strange, it's a slightly unique to Vulkan way of programming. So it's important to just keep, thinking it through, keep thinking through the same concepts, make sure that you're sort of rock solid on them because it's important. And this is where a lot of the sort of performance benefits are. Anyway, hopefully this sort of lays things out very clearly. In the next videos, we're going to be jumping into the code and actually implementing this, but I just wanted to give this overview first of all. Anyway, have a good one, and I'll see you in the next one. Bye.